Hello and welcome to my presentation on work we did on redirected walking in virtual reality, and specifically on the effect of spatial audio on curvature gains in virtual reality redirected walking. Together with other authors, we've worked on this for quite a while, and I'm happy to share with you what we found. The structure of this presentation will be as follows. Uh, I'll first explain more about locomotion, on the problem we face in virtual reality, and what redirected walking is, and then the research we have done. So the experiment we set up, the results we found, and how we analyze them, the implications of these results, the limitation of our research, and then the conclusion. So let's start. So in virtual reality, we can explore unlimited environments which go beyond imagination. However, when we want to navigate these virtual worlds, say for example this big open football field, our natural movement is limited by the constraints of the physical space that we are in and its obstacles. So free locomotion in the virtual world is a major hurdle to take. Besides the hardware solutions, which can be expensive, or controller-based locomotion which can lead to nausea, there is a technique called redirected walking, or RDW for short. Essentially, redirected walking involves subtly changing what users see in their VR headset to trick them into moving differently without them realizing it. So for example, they may experience that they are walking straight in the virtual world, while they're actually walking following a curved path in the physical world. In an extreme application, the user could walk on an infinite straight path in VR, while actually walking around an infinite circle in the physical world. In this case, the user could walk freely from goal to goal. There are different types of redirected walking, and in this study we focused specifically on curvature gain, which is the described application of manipulation where every meter of distance the user moves forward, a degree of rotation is applied to the virtual environment. This is expressed in degrees per meter to allow for comparison between studies. However, there is a limit to how far this illusion can be pushed before the incongruence of senses is detected, and this is called the detection threshold. So how does redirected walking work? Well, this technique works partially because of multisensory integration. Human perception relies heavily on the input from various senses. Among these, the vestibular, visual and auditory systems play a crucial role in helping the brain orient the body and maintain a sense of space. Due to the visual dominance, redirected walking can be achieved by visual cues alone. To ensure a coherent perception of space, the body unconsciously generates movements to compensate for the perceived motion, and this phenomenon allows for application of redirected walking. We wanted to find out if the illusion of walking in a straight line can be enhanced, making it harder for users to detect the manipulation. Adding spatial audio elements can enhance the illusion already created by the visual cues, making the illusion even more convincing to the brain. Previous studies have explored the use of spatial audio in redirected walking under specific conditions, such as different strengths, called the gains, for various types of redirected walking compared to curvature gains, or by solely focusing on the audio part. However, there is a gap in the research regarding the comparison between visual only and combined visual and audio stimuli for curvature gains. This comparison is crucial for understanding the impact of spatial audio on perception thresholds related to curvature gains in redirected walking, especially about the use of spatial audio and the feasibility of implementing redirected walking in various virtual applications. Okay, then on to our research. We have conducted an experiment to test our main hypothesis, which was that adding spatial audio elements significantly decreases the detection percentage in curvature gains for redirected walking. We did this in a within subjects experiment with 18 participants, where each participant was tested under conditions both with and without audio to see how spatial audio affected their ability to detect the curved manipulation in the redirected walking. Participants were placed in a virtual industrial environment and were asked to walk in a straight line to a target, which was a few meters in front of them. And while walking, the virtual world was rotated to apply the redirected walking. Each time after reaching the goal, the participants were asked to indicate if they had walked to the right or to the left in the real world. If they experienced moving neither left nor right, they were to choose the answer that felt most correct. And this setup follows the two alternative forced choice method of measuring detection levels for a given signal. Then here are the conditions we used in our experiment. The conditions varied in the strength of manipulation, with the strengths being 0, 3, 6 and 9 degrees per meter to both the left and to the right, and each trial of course had a version with and without audio. The audio consisted of different audio landscapes being placed on the right and on the left of the participant, and a beeping sound coming from the target object. For statistical reliability, all the conditions were repeated multiple times, and all conditions were of course random. And the zero condition was a control condition, as the answers there should be around 50% to the right and 50% to the left, as there is no manipulation applied. Then we had to get from the walked paths the provided answers by the participants all the way to a detection threshold. When we plot the participants' walked paths, we can clearly see that the effect of the applied curvature gain to both the left and right works very well. The different colors here indicate the different conditions. Now that we see that the manipulation works, we combine the walked paths with the provided answers to see when the participants noticed the manipulation. Okay, so the results. We wanted to see if the application of spatial audio also leads to a lower percentage of correct answers for each condition. We have used a 95% confidence interval, and this is the table showing the results for each condition. We see that at each curvature gain, the percentage of correct answers was lower for spatial audio, shown in the column on the right, compared to the conditions without spatial audio, which is shown on the left. Thus, it was more challenging for participants to detect the manipulation, suggesting that manipulation was more convincing. Next, we calculated the accuracy percentage under the different conditions, which was analyzed statistically using a 3x2 repeated measures ANOVA, with the vectors gain, 3 versus 6 versus 9 degrees per meter, and if spatial audio was on or off, so the audio versus the no audio condition. Our analysis revealed two significant findings. Firstly, there was a significant main effect for gain, with an f-value of 8.593 and a p-value of 0.004, with an effect size of 0.336. indicating that the manipulation gain significantly influenced the participants' responses. Secondly, we found a significant main effect for audio, with an f-value of 7.467, a p-value of 0.014, and an effect size of 0.305, suggesting that the presence of spatial audio also had a significant impact on participant perceptions. However, the interaction effect between gain and audio was not significant, at 0.762 with a p-value of 0.474 with an effect size of 0.043, indicating that the combined influence of gain and audio did not differ significantly from their main individual effects. So regarding our hypothesis, we could confirm that spatial audio significantly decreases the detection percentages. Now, in order to find the detection threshold, we fit a psychometric function to the found individual detection percentages to approximate a natural function for detection. And with this, we derive detection thresholds by determining a point of subjective equality, where participants can correctly determine, beyond chance, if their real-world path is manipulated to the left or the right. We fit the psychometric function for the detection percentages for audio and for non-audio. The curve shows that the experimental data had a good fit for the condition without audio, with an R-squared of 0.990, and with audio condition with an R-squared of 0.981, which suggests that it is an appropriate representation of the data. And now, using this function, we've assessed the detection thresholds using the 75% detection rate. And this resulted in the detection threshold of 6.20 degrees per meter for the condition without audio and 8.78 degrees per meter for the condition with spatial audio, highlighting the potential effect of spatial audio. Then on to the potential causes. To understand this found effect, it makes sense to go back to the multisensory fusion. A cause can be that the spatial audio elements are used in the maximum likelihood estimation in the brain we've discussed before, in the same way as natural audio cues, strengthening the redirected walking illusion. As a result, users may find it harder to detect the redirection, leading to fewer correct responses. Another potential cause could be that the presence of audio might divert attention from the task of walking straight and detecting a manipulated path, increasing the cognitive load and reducing detection ability. In both cases, adding spatial audio does raise the threshold for detection. Further explanations are of course also possible, so those should be explored in future work. The implications of these findings are interesting when looking at the effect of the minimum diameter needed for curvature manipulation, which is undetectable for the user. Without audio, this diameter is 18.47 meters, but when applying the audio, this diameter can be reduced to 13.05 meters. So, our study provides empirical evidence and we have quantified the effect of spatial audio in curvature gains for redirected walking. Then there are of course limitations to this research. Firstly, the sample mainly consists of individuals from the Netherlands, representing a so-called weird population of Western, educated, industrialized, rich and democratic participants, which potentially limits the generalizability of the findings. The narrow age range of 22 to 28-year-olds and predominantly male people in our sample further restricts the applicability of the results across different age groups and genders. Additionally, the reliance on specific hardware specifications, such as the Meta Quest 2, which we used at a refresh rate of 72 Hz, introduces uncertainty regarding the comparability with previous studies and its effect on manipulation detection ability. Our study also focuses on a specific set of sounds, which also limits the insight into other sound types. Finally, potential learning effects should also be considered as a possible limitation of this research. So, to conclude, we found a significant effect of spatial audio elements leading to manipulations that were harder to detect for the participants. And this suggests that, yes, the addition of spatial audio elements leads to a higher detection threshold for curvature gains of up to 8.78 degrees per meter, which is an increase of 2.58 degrees per meter when compared to the condition without the spatial audio elements. And this in turn implies that the circle with a diameter of 13.05 meters is required to successfully apply an undetected curvature gain to a redirected walking experience in these virtual environments. So therefore, spatial audio is a simple but effective approach to strengthen manipulations in redirected walking, which enables natural movement in VR while in a smaller physical space. So, thank you for your attention.